Good morning. We will be continuing with what we started about the refineries and the various downstream chemicals which one can get starting from crude oil or natural gas. Last time we discussed how the very important steps are. One is the crude oil distillation and how that gives you some broad fractions and which are further fractionally distilled, to get many more different product streams. And we also talked about the importance of doing some kind of purification in terms of getting rid of things like sulfur and nitrogen, so all this hydrodesulfurization process, etc. We did see that one of the things that you get even before putting it into the crude distillation unit is that one flashes of volatiles, and those volatiles are typically low molecular weight substances. A refinery might also bring in natural gas, raw natural gas, into their factory. So one of the things that is first done is that one takes out methane. After that, one might be left with things which can be converted into propane and butane and things like that, and use the methane for different purposes, whereas these will be subjected to cracking, some kind of a cracking, and then you might actually want to generate unsaturated compounds from these, like ethylene, propylene, benzene. You may want to do that, butadiene. So all of those kinds of things can come from the raw natural gas, so that fraction which is not methane. Or one could even take the crude oil, and from the crude oil we saw from the top you got naphtha. Naphtha is a very good feedstock. Then we saw the gas oils. Like if your intention is to make more lighter, low molecular weight compounds, which are required further downstream, then you might want to do that. Prior to that, you may want to distill off the benzene, toluene, xylene, BTX. You don't want to crack those because these have big applications. So first take those out, and the rest of it you might want to just put it into the cracker and basically break it up into smaller components or into the unsaturated fractions. Now, we've already seen when we studied the Haber-Bosch process, how natural gas was extremely important for producing syngas by steam reforming. This methane, a lot of it actually goes for steam reforming in a refinery. Why? Because when I reform, I'll get carbon monoxide and I'll get hydrogen. We will talk about the where all carbon monoxide is used for, and hydrogen that's required, for example, in the hydrodesulfurization and removal of ammonia, nitrogenous substances, etc. You need to do that treatment with hydrogen. So hydrogen is extremely important in a refinery. We have already learned about production of syngas, so I will not go through that. But now, while in the case of ammonia, we use the syngas through the primary reforming to further expose it to air, and then we did an air reforming, and whereby we introduced the nitrogen, basically the nitrogen and the hydrogen and carbon dioxide and some water. These were the ultimate components which we got. And then we discussed how you can do a water gas shift, increase the amount of hydrogen and also convert all the CO into CO2, and then how the CO2 and the water can be taken out, and then you are left with a relatively pure mixture of hydrogen and nitrogen, which is what goes further downstream into the production of ammonia. Now, what you can also imagine is that you see, I can actually take the syngas and also make methanol. That's all I require. CO plus 2H2 will give me methanol. Also, there are ways of combining CO and H2 by the Fischer-Tropsch method, and you can actually make fuels from the CO and H2. So you can make C12 fractions, C10 fractions, long chains. All of that is the Fischer-Tropsch chemistry, which we will not discuss. But this was actually recognized by BASF almost soon after they had developed the technology for making syngas from natural gas and coal. That why don't we try to expand the utility of this stream that we get after steam reforming? Very soon after, I think within a couple of years, BASF actually came up with a catalyst, zinc chromide, this one. You can see it's like not very different in terms of the pressure and temperature compared to what we have in the Bosch process with about 200, 300 bar and 500 degrees centigrade, or 300 to 500. So very similar. So they obviously had managed all the chemistry around production of ammonia. So it was a very logical extension of that work to make methanol. Only thing is that they had to develop a catalyst because obviously the catalyst for ammonia synthesis is very different from the catalyst for methanol synthesis. So obviously there was a huge amount of effort that went into inventing this particular catalyst. Now you can also see that all of these reactions, whether you make it from CO or CO2, they are all, or from water to get first this, and then you can react it with the hydrogen to get methanol. That all of these processes, steps are all exothermic, all of these. So it was very logical for them to really extend the concepts that we have learned, for example, in the sulfuric acid process or even in the ammonia process, because that's also exothermic, that how you run it adiabatically, then cool it, again do the next stage adiabatic reaction and continue. So they basically adopted very similar chemistry and they were able to produce methanol. And you can imagine that methanol is again a very, very big bulk chemical. And so it was a huge breakthrough, the production of methanol. And of course, because it is an exothermic reaction, people were all the time trying to see if they can reduce the temperature at which the reaction can be carried out. And also, they were trying to do it at a lower pressure. Although, of course, pressure would favor this particular reaction. So there was a huge effort made to try and reduce the temperature and pressure in the production of methanol. And the people who were able to succeed in it was ICI. They were able to make a mixed oxide. Of course, this is also a mixed oxide catalyst, chromium oxide, zinc oxide, but of a different kind. What was remarkable is that this was developed in the 60s, whereas the methanol process originally developed by BASF would have been somewhere around 1920, around that time. So we are talking about a good 40 years after that, that this new catalyst was made. And remarkably, this catalyst could operate at 50 bar. You can imagine from 300 atmosphere going down to 50, and a lower temperature also, 200 to 300 degree, whereas this was 300 to 400 degrees centigrade. So it was a huge breakthrough, and obviously the capital investment in setting up these plants naturally came down, and they were able to actually make even smaller plants. What they also found is that they did not compromise in any way on the rate of the reaction. If anything, both the conversion and the rate were tremendously accelerated with this catalyst. And so effectively, this is more or less the same technology which world over would be practiced. Of course, now other people may have developed their own catalyst, but this was really the after the BASF work, certainly the biggest breakthrough that was achieved in the methanol synthesis. The other thing which we did is not just about rate and conversion. The selectivity with which they form methanol was also much better. So name it whichever way you want to name it. It was a very superior catalyst. I'm not going to go through this detailed process, but for those who are interested, you can have a look at this whole process. The sum and substance is that this is really broadly the kind of chemistry that is followed in this particular process. This is your main converter. You have to basically take in syngas, and then the syngas is heated up and then circulated in this, and this is where your this catalyst will be. And then you carry out the reaction. Naturally, you have to cool the outgoing methanol, and so that's where the heat exchanger comes in. So you're cooling the outgoing methanol and you're heating up your incoming feed. And then the rest of it is, some of it will be related to purification, etc. Now, methanol, of course, was a very, very important breakthrough because after methanol was produced, people also realized that in syngas, I'm producing also carbon monoxide. And especially if I'm using hydrogen for my hydrodesulfurization and all the other hydrogenation related chemistry, that I will have surplus carbon monoxide. And so, people started looking at what all can I do with carbon monoxide. One of the very, very important breakthroughs that happened is acetic acid synthesis from methanol. Now, can anyone tell me what is the difference between, just look at the structures between methanol and acetic acid. What is the difference between the two? What is extra in the acetic acid?
And oxygen?
Only oxygen? Well, acetic acid is 2 carbons. Methanol is 1 carbon.
Carboxyl group.
Carboxyl group.
So yes, sir, the C double bond O.
You are missing a CO, C double bond O. So what people thought is that look, if I can somehow insert CO into methanol, then I'll basically have CH3CO OH, right? So that became a very, very hot area of work. In acetic acid, you have got a carbon-carbon bond, CH3CO2H. So obviously the carbonylation had to take place in between the CH3 and the OH. So that means you have to insert CO between the CH3 and the O. Is that clear to everyone?
Clear, sir.
Let's just write it down. And then I'll put another OH. So just think of CH3 over here, and you've got your OH. These are all coming from methanol. And so I've just got to slip in a carbon monoxide between the CO bond. So that's what I have to do to make acetic acid. And this was one of the greatest processes which was ever made. And it was by Monsanto. It's one of the earliest examples of homogeneous catalysis, organometallic chemistry. Okay, we have learned about homogeneous catalysis when we talked about the chamber process, but these are all metal-based homogeneous catalysts. Earlier, all the focus was on heterogeneous catalysts. But people also realized that there are certain advantages of having monomolecular species rather than these kinds of solid state catalysts, simple molecules. So they were able to actually identify this this particular catalyst, you can see it is rhodium with 2 carbonyls and 2 iodides, and it's in a -1 state. The 2 I's basically are I minus, and carbonyls come neutral. Carbonyls attaching themselves to a metal, it's always assumed that the oxidation state does not change. But when you are forming a sigma bond, and I'll explain that to you, then there is a change in the oxidation state. So obviously this is a minus, so that means rhodium must have been +1. So +1 and -2 will give me a net charge of -1. Now, what they did, it's a remarkable process. They found that methyl iodide adds across this rhodium. Over here, you can see methyl iodide has added. Now, this particular process of addition is known as oxidative addition. So, these are the two standard terms which are extremely important in the catalysis of organometallic compounds. When they add like this, it is known as oxidative addition, and there will be a net +2 change in the oxidation state. So it's going from rhodium 1 to rhodium 3. Okay, this is 3. And you can also have the opposite. When from this, you could actually remove methyl iodide, for example, and then if it came out, then that would be called as reductive elimination. So these are the two very, very important terms. I remember when I was doing my PhD and the person who was teaching us organometallic chemistry, he would always say, remember these and know how to count your electrons.
So please could you repeat that part, so oxidative and reductive
so what
parts?
happens is that, there are two things. You can see this rhodium is in the +1 state, and also that it has got 4 coordination around it. Rhodium can exist up to a 6 coordination comfortably. In some compounds, it is at a high coordination, but getting a octahedral coordination is not a problem. So it is, in that sense, it is coordinatively unsaturated. So I can add things across the rhodium. And the second is that when I take a compound like this and I add, it is assumed that the methyl and the I are given a formal oxidation state of -1. That's it. So basically that is compensated by a formal oxidation state of rhodium, which is +3, naturally, because these are taken as -1. Iodide is easy to understand why it is this. But that kind of a concept came from things like butyl lithium, or even in the Grignard reactions. These were basically where the organic part was considered to have a negative charge and the metal was assumed to have a positive charge. So that is really the reason why formally these are indicated as minus charges, and therefore the rhodium becomes +3. Is that clear now?
Yes, sir. Thank you, sir.
Okay. Now it has got coordinatively saturated and is gone into a rhodium +3 state. Now, this is where organometallic chemistry has played a revolutionary role in many processes, and it's typically, I will say, it's from 1955 or thereabouts, 55, 56, and after this we'll be also discussing another very famous process. So, what was found was, of course, this is all mechanism, but there's been enough study done to actually validate this mechanism. What they found is that the methyl group, now it transfers itself to the carbonyl. And now what happened is that you actually have a rhodium carbon bond. Okay. Now, so this is a sigma bond which is being formed, and the oxidation state of rhodium doesn't change because, as before, what you have is these are 1, 2, 3, 3 minus charges from here. 1 minus charge will come from this organic moiety, so that will be -4. There is a residual minus charge, so it is rhodium 3. So effectively there was a transfer of methyl to the CO, and that is basically the carbonylation chemistry. Now what happens is they purge CO through this system. And when they did that, because it's coordinatively unsaturated, another CO effectively came and got bumped. Now, what the molecule says is that I want to go back to my original state. And so, when I go back to the original state, what I'm doing is that I'm doing now a reductive elimination where I'm getting CH3CO and this I. Instead of the CH3I, it's now CH3COI. That is what is coming out. So I reductively eliminated, and now when I do a reductive elimination, my oxidation state reduces by 2. So the rhodium 3 went back to rhodium 1, and I now have 2 iodides, I have 2 carbonyls, so I've got back my original compound. So what this did is a beautiful shuttling job where it was able to bind both the CO and the, well, not really methanol, methyl iodide, okay, and then it got a transfer of the methyl from the metal center to the carbonyl. So now what happens is that I formed MECOI, and MECOI, I just need to hydrolyze. The moment I've hydrolyzed it, what will I get? I'll get acetic acid and I'll get HI, okay, when I add water to it. So that's what I'll get. I got my acetic acid now, and I've got my HI. This HI will react, by a simple SN2 mechanism with methanol, and it will become methyl iodide. What will I form? I'll form water. That water goes back here. So effectively, that methyl iodide is what is adding to this catalyst. So look at the interesting way in which it is done. And what were my net consumables? What did I consume? I consume methanol and I consume CO. Everything else is going back and forth, and I produce MeCO2H, which is acetic acid. Ultimately, I did a carbonylation of methanol and ended up making acetic acid. Is it clear to everyone, the mechanism?
Yes, sir. It's clear.
Okay. Although it was such a breakthrough, there were some problems with the rhodium-based catalyst. One was that we saw that it generates HI. Now, what they found is that it can end up also forming hydrogen. Some amount of hydrogen ended up being formed in this particular process. And what that hydrogen was doing was that this rhodium catalyst not only did the carbonylation chemistry, but it turned out to be quite efficient at also doing hydrogenation. So effectively what was happening was that when it transferred over here, you see, if I do a hydrogenation of this carbonyl, I'll end up forming CH3CH2. So it is like as if I've added CH3CH2I. And now when I again add carbonyl and do the carbonylation, I'll end up forming now propionic acid rather than acetic acid because of that. So propionic acid became a side product which you don't want. You want it to be much more well controlled, that you're getting exclusively acetic acid. And so that was one of the things. They also found that in case there is a deficiency of CO, that the catalyst then becomes quite unstable. So that was another very important thing. And what happened was that what they also found is that this particular reaction is favored when you have relatively low concentrations of methanol and more water. In other words, the productivity of the catalyst in that sense was a bit limited because of these kinds of issues. And so what now happened is something very, very interesting. Now, when something like this happens, and if you are trying to do research, what might you do? What kind of playing around can you do and considering all the things that we have discussed in this course of some kind of a playing around.
So change the catalyst.
Change the catalyst means change what? Stick to rhodium and change the catalyst, or stick to the basic structure of the catalyst and change the metal?
So stick to the basic structure and change the metal, or CO
Fantastic.
can be replaced.
To the same broad structure of the catalyst and try changing the metal. That's what you're saying.
Yes, sir.
And nobody knew actually what will happen, and that's exactly what was done. So what happened was, just like we saw how Haber cleverly found osmium in place of iron, and later on the Japanese did excellent work on ruthenium catalyst for ammonia. So if you look at this, you've got cobalt, rhodium, iridium in this group. So it's not so unusual to try and play around. And that playing around was done by British Petroleum. Look at this. All the work, the novelty, everything was done by Monsanto, conceptualizing such a brilliant scheme. And what did British Petroleum go and do? They just changed the rhodium to iridium. Look at this. Nothing else is different. Same things, basic thing. Only instead of this, they went to the next element, iridium. Same chemistry as we saw. Nothing is different. They were master copycats. They just did this. But what happened was that there were huge improvements when they did this. What were the improvements? One was is just amazing. Look at this axis, okay? This is the carbonylation rate. We're talking about the carbonylation rate. What they found is that whereas the rhodium catalyst had this kind of a behavior where higher concentrations of water favored the reaction, but in the iridium case, okay, and also with ruthenium, mind you, but anyway, largely it is iridium based. What they found is that actually the catalytic rate firstly was much higher than with rhodium, and secondly, just like we had found, when we looked at the platinum rhodium catalyst for converting ammonia to NO, we found that a little bit of rhodium actually improves the properties of the platinum. It improves or reduces the loss of platinum, and it also improves the overall conversion. Here, what happened was, again, very interesting. One, it basically increased the rate of the reaction, and it peaked at a lower concentration of water. In other words, I could now take much more methanol. I mean, it was just amazing. Okay. And the second was that because I could take a lower amount of thing, so my rate was higher, and obviously my throughput was also higher because I could push more methanol per cycle. So there was a huge improvement. And so Monsanto's rhodium-based catalyst got phased out. And this is known as the British Petroleum's Cativa process. It's a very famous process. Okay. The other very interesting thing is that, like over here, they also looked at the rate equation, and the rate equation was different for the two. So just like we have seen with the platinum and vanadium pentoxide catalyst, that the rate equations are different. So the advantages were that catalyst is robust and stable even at very low water concentration. Hence throughput can be high, and also the rate of the reaction was high. Oxidative addition of methyl iodide to the metal center is 150 times faster, which represents a dramatic improvement in the reaction rate. In other words, this oxidative addition of methyl iodide in some ways was the rate limiting step. So that actually got kind of overcome with the iridium catalyst. So now you can see how, starting from a simple natural gas, methane, making syngas, making methanol, and then ending up with acetic acid as well. And you know how important both methanol and acetic acid are in a wide variety of chemistries, okay? Esterification, this, that, name it.
I had a small doubt, sir.
Yeah.
So, while covering the RH, the rhodium catalyst, you mentioned that low concentration of methanol is required.
Because I need more amount of water. Obviously,
Oh, okay.
if I have one more than I have to have the other less as a percentage.
Okay.
Okay?
Yes, sir.
Let me ask you, if I had to again look at this carbonylation chemistry and like I want to make formic acid. How would I make formic acid? What would I add carbon monoxide to or insert it?
So hydrogen.
Hydrogen and just hydrogen. No, then I'll get formaldehyde.
Water.
Water. Last time we inserted the carbonyl between the methyl and the oxygen. Okay. Now, if you insert the carbonyl between the oxygen and the hydrogen, then I end up with HCO2CH3, which is what? Which is basically the methyl ester of formic acid, right?
Yes, sir.
People were then able to actually find, of course, a different catalyst, that it is not the rhodium or iridium based catalyst. They were able to take sodium methoxide, a base, as a catalyst, very dry CO, and with 96% selectivity, they could make methyl formate. Now, you will also understand sometimes, how tricky workup can be. Like methyl formate, you would think that you're almost there. What is there? I mean, I'll hydrolyze and I'll make formic acid. But it's a problem because the formic acid and water, formic acid, of course, dissolves in water, and formic acid and water have very, very similar boiling points. And so to separate out formic acid from water is quite difficult. So look at how they went about doing it. Just to manage that problem, they first took the methyl formate and then reacted it with ammonia, formed formamide and methanol. They recycled the methanol into this process, again did carbonylation, got back methyl formate. Then they took the formamide, reacted it with sulfuric acid, made formic acid, and ended up with diammonium sulfate. Diammonium sulfate, of course, is a very good fertilizer, so they didn't mind producing it. But can you imagine the complexity in trying to recover this? Because here I didn't have the problem because diammonium sulfate is a solid. By the way, there was a lot of interest in formic acid because I think it was in the 40s, it was found that formic acid has a remarkable property that if you take green fodder, you can keep it stable and store it for a long, long time just by adding some formic acid into the fodder. So that became a big thing because it was one of the very important interventions in agriculture at that time. And in fact, the person who worked out why all this happens actually won the Nobel Prize in 1945 for his work. So it wasn't a trivial thing. And just look at the complication. This whole thing, where you are adding the sulfuric acid, you are getting this, and then you are trying to remove the formic acid, is all done in a rotary furnace. And can you imagine the rotary furnace? There is a train track which goes through this. And the reason is because, this ammonium sulfate tends to stick to the sides of the wall. Okay. And so you need to actually scrape it out. And so, they had to have scrapers and they had to keep scraping out the ammonium sulfate. And just imagine how complicated this whole thing is. Why? Because I'm trying to recover formic acid, and formic acid has similar boiling point to water. So I cannot just do hydrolysis and take it out. I hope you understand the importance of physical properties, knowing boiling point, melting point, this, that, and then, sometimes it can come to your assistance, and sometimes, it can thwart your plans of what you want to do. In fact, it's interesting, I was looking the other day at the freezing point of formic acid. In fact, when I was preparing your lecture, and I found the freezing point is 8.3 degrees centigrade. I was just wondering, whether maybe if they tried to freeze it, whether you might be able to actually take out the formic acid as a solid. I don't know. In fact, it will be a beautiful experiment for someone to do. If you're looking for, clever things to do, and on a Friday afternoon, try things like this. It's a lot of fun. Most probably you'll fail. You'll probably find that the water is occluded in the formic acid. But who knows? If you succeed, what a brilliant thing. But that's not the route that BASF took. BASF said, okay, the boiling points are similar, but chemically, water and formic acid are not identical, they're different. And they started research on looking at extraction techniques. Is it possible to extract out formic acid from a water formic acid mixture? And in fact, I was reading this paper, and obviously one of the solvents that they were able to identify was butyl acetate. Butyl acetate doesn't dissolve in water, but it's a tricky process because butyl acetate can get hydrolyzed in the presence of formic acid in water. Because in acid, you've got water. What's so difficult about doing it? So obviously, there must be a lot of tricks around doing it, or maybe it is not butyl acetate; it's some other hindered ester which doesn't get hydrolyzed very easily. Maybe that's what they do. Something tells me that it's a little more tricky than just taking butyl acetate. So they were able to extract it out. And once I've extracted, what's the issue? There's nothing. Then I just distill off my formic acid. Most probably the solvent had a higher boiling point, and they got pure formic acid. And look, got it without generating all this stuff. Remember what Davis said, that it's better that you don't generate the waste than trying to utilize the waste. And look at this, it's a zero waste process. There's nothing else. I'm just hydrolyzing, getting back my methanol. I'm again doing carbonylation of methanol. So what am I doing? I just need carbon monoxide, that's it. Nothing else. And you can see it's it is something where they succeeded in 1981, not 100 years ago. So we've looked at least one aspect of natural gas and how it was value added, and how from that you get CO plus H2, and then you get methanol from that. From the methanol and the CO, you get acetic acid, or you can add CO into methanol again, but adding across the OH bond, and that gives you formic acid. I mean, I hope you can see the cleverness and the innovations that go into industrial engineering and processes. That's why these things are so marvelous.
Excuse me, sir.
Yeah.
So I wanted to ask that instead of extracting it out, so does formic acid dimerize or trimerize in some kind of solution so that it solidifies out, crystallizes out?
Very interesting. Like you're talking about like glacial acetic acid. It's a beautiful idea. But then I don't know. I'll have to see. If it was, I'm sure these guys would have been aware of that. Probably doesn't. But it's conceptually a very good idea, it seems to me. Let me just put it down because it's such a good idea. N1 can one look at alternatives to extraction? This is another thing that I would advise you all to also look at. If you're proposing an alternative, like you saw the Cativa process, there was clearly a problem, okay, with the rhodium-based catalyst, or I wouldn't say problem, there was an opportunity to improve. You will have to see what is the problem with separation by extraction and what is the solution that you're trying to devise. I mean, you can develop an alternative, but that doesn't mean that the alternative will be in any way better than extraction. Is that clear?
Yes, sir. Thank you, sir.
Now, let us look at ethylene. We saw that any of these things, when you do cracking, you can get many very important compounds like ethylene, propylene, acetylene. These are the primary building blocks from which you can make so many different compounds, as you know. And like you look at ethylene and propylene, and then you're talking about polyethylene and polypropylene, the number 1 and number 2 polymers, which I think between them will be easily 200 to 300 million tons, that kind of a figure. So it's huge. So what is done, and this cracking process, we saw the 4 operations in a refinery. One of them is the reactive block. This is, of course, the reactive block where you're doing such cracking. Now, this cracking can be done both thermally and also catalytically. So there are different ways in which you can do it. And an excellent feedstock for doing cracking is naphtha. You saw the naphtha is the lighter ends which came off at the top of the crude distillation unit. That's naphtha. Naphtha is typically a C4 to C11 mixture of hydrocarbons, straight chain hydrocarbons, cyclic paraffins, even some aromatic hydrocarbons. And if these things are within a boiling range of 35 to 145 degrees centigrade, then it's called light naphtha. And if it is between 145 to 200 degrees centigrade, it's called heavy naphtha. So obviously, those are the kinds of things you'll be separating out after the fractional distillation, which follows from the crude distillation unit. These things normally, this cracking take place at very high temperatures. You can see over here that the cracking temperatures 500 to 680 degrees centigrade, it's very high. Now, what happens is that once I have cracked, like let's say I've cracked naphtha and I've made ethylene. Now, obviously, ethylene itself is also something quite reactive. So it can easily polymerize and I can get all kinds of products from there, unwanted. I don't want those. And so you can get C4, C5, C6. All of these products can form if you do not control this process. So how is it controlled? Let's look at a few things which they do. So firstly, you have to remember that it's an endothermic reaction. It requires large amount of heat to carry out the cracking. Now, typically what happens is that you need to maintain a short residence time so that the further reactions don't occur. Second, obviously, most of these other reactions which will take place, naturally they will be promoted if their concentrations are high. Obviously, if I'm going to form a polymer or a dimer or trimer of ethylene, naturally higher is the concentration, more this will happen. And the third is the temperature. I have to do something about the temperature. So what they do is they really play some great games. One is they use, because these are all taking place in the gas phase, right? These are all vapors, and so at that time they introduce steam, and when they introduce steam, steam becomes like a diluent, and it just dilutes these volatiles, like ethylene, propylene, etc. So that reduces the probability of further reaction. That's one. Second is, we know that, for example, whenever you do any cracking, there's always a possibility that you will end up with some amount of coke formation. And this is a huge problem. And if you have then your catalyst, everything will get completely messed up. So what we know is that if you take, for example, you've got coke and if you've got steam, then they will react. And again, I will do steam reforming and end up forming CO and H2. So what will happen therefore is that I can actually prevent the coke formation by introducing steam. So steam serves two purposes. One is that it dilutes the products which are obtained, and the second is that if any coke is formed incipiently, it will immediately react with that coke and basically convert it into syngas. So that's what you'll have. It says over here, steam helps to reduce coking deposits by reacting with coke to CO2, CO and H2, and also reduces the catalytic effect of the reactor coils, metal walls, which tend to promote coke formation. The walls of the vessel, they are also catalytically active, and what the steam does is that it kind of deactivates the metal walls through this kind of operation. Now, the other thing that you have to do is that's not all. You need to, even with all that, it's great. I mean, you can control, but you need to rapidly cool it. So imagine you're heating it at a high temperature, it's cracked and freeze, rapidly cool it down. That's how they really are able to arrest the formation of all these secondary reactions. They will always take place. It's a question of to what extent. The things which are like saturated, ethane, propane, etc. From this you might take it back over here. Some of the gases will go into actually combustion and provide the heat which you require for the cracking process, and part of it could actually be recycled as feedstock along with fresh naphtha. And the rest of the stuff, whatever you require, that will be effectively taken out. It will be compressed, and after that you can carry out further separations of some of these products, and you will get your ethylene, propylene, etc. In separated forms. Now, as I was telling you, the global market of ethylene in 2020 was close to about 160 million tons. You can imagine it's big, and how important. Of course, we talked about polyethylene, but so many other compounds. You reacted with chlorine, you will get dichloroethane. From that, you will get your vinyl chloride and polyvinyl chloride, all the PVC pipes, etc. All your refrigerants will come from some of this. From ethylene, you can make ethylene oxide, polyethylene, vinyl acetate. We'll discuss these. And those in turn, ethylene oxide, you can hydrolyze to ethylene glycol. That goes into all this engine coolant, making polyester. So you can imagine, and ethylene oxide, all the people who make surfactants, one of the things is that you need polyethylene oxide EO chain, and that's what increases the hydrophilicity of these molecules and converts it into a surfactant. So ethylene oxide actually plays a huge role even in preparation of detergents and various surfactants. So that's the totality, and therefore you can imagine that this is a classic example of a platform chemical, because once I've got it, I can launch myself in so many directions. There's no end. By the way, you can also hydrate ethylene and make ethanol. We talked about dehydrating ethanol, which you get from renewable sources through fermentation, and then you dehydrate and make ethylene. But people have also done reverse, because the reverse reaction is an exothermic reaction. This dehydration is an endothermic reaction. This is an exothermic reaction. So people actually make ethanol. About 7 to 10% of ethanol is actually made from the hydration of ethylene. So I hope you can appreciate the importance of these things. This is just to show you, how ethanol is made. As I told you, it's an exothermic reaction. You can see not very strongly exothermic, and this is the catalyst which they use, phosphoric acid catalyst. Now, because hydration means that I have to add water, and these acid catalysts can actually dissolve in the water. So when this reaction is done, it is done with substoichiometric amounts of water. With that, they minimize the chance of the dissolution of the acid, and the water gets taken up in doing its main job, which is the hydration to ethanol. Again, because I'm taking a substoichiometric amount of steam, so obviously I'll have to recycle the whole thing. So what they do is typically these kinds of reactions, in a single pass, barely about 5 to 10% of the reaction takes place, and the thing is recycled many times, as we have seen in so many processes, like whether it is ammonia or N-oxide, etc. So many chemistries are based on recycle. Let's come to another very classic process and product, which is ethylene oxide. When ethylene oxide was made initially, again, who else but BASF, a process was invented by the French. And mark this year, because I'll show you why it is so important, 1859. What did they do? They did very linear process, very linear kind of a thinking. They thought that you can take chlorine in water, it forms HOCl, that's known, and HOCl can add across a double bond. So I'll form this. But problem is that because chlorine is also present, so chlorine can also go and attack the ethylene, and I'll end up with dichloroethane. This is like a dead end. When I want ethylene oxide, this is not something that I really want to produce. So what they then did is that you take this stuff over here, you react it with lime, and what will it do? It will form calcium chloride, because I'm effectively just pulling out HCl. And so I'm pulling out HCl and I'm neutralizing with lime. So it will form calcium chloride and water. That's effectively what I'm doing. It's not a bad process. Certainly, if you ignore the dichloroethane formation, if you consider from here going to here, ethylene oxide, you can actually do it with a 95% conversion. So this step is very efficient. But you can see that for 1 ton of ethylene oxide, you end up forming about 200 kg of dichloroethane. Now, if one has a use of dichloroethane, no issue. You can separate it out and sell it as another product. We learned about when we were looking at the Leblanc process, that try not to form these things. That is the best. If you can avoid their formation, always the best. And it was much later, 1931. So you're talking about 40 and 30, 70 years later, that a new process was invented, again by the French. That's interesting, okay? And after all, what is the job of chlorine? What is chlorine doing? Actually, if you broadly look at it, finally look at ethylene oxide and chlorine. What is the role of chlorine? Well, it is actually acting as an oxidizing agent, because finally I'm ending up with ethylene oxide, which is an oxidized form of ethylene, and chlorine is an oxidizing agent. So obviously, that oxidizing agent is coming because of the formation of HOCl. So indirectly, chlorine is actually doing the oxidation. Now, people started looking at that, is it possible to oxidize ethylene directly with oxygen? That's what these people were looking at. This is a thermodynamically favored process. It's a delta H, you can see, minus 106.7 kilojoule per mole. Not bad, but problem. Almost like when we were looking at the ammonia oxidation to NO, and we saw, some of it can form nitrogen, and those things were far more exothermic reactions than your desired reaction. Exactly the same thing is true over here. That ethylene, if you look at the thermodynamics of it, that this is minus 1323 kilojoule per mole. This reaction, which is basically just the straight combustion of ethylene to carbon dioxide and water. And also, ethylene oxide can also get further oxidized to get carbon dioxide, and in that sense, you can look at ethylene oxide as an intermediate to formation of CO2 from ethylene. What these people were able to do was that they were able to control the oxidation of ethylene, and they were able to actually take out ethylene oxide as a product. Ethylene oxide is not as big as things like ethylene, but 26 million tons is not a small amount which you require. And as you saw, ethylene oxide is required to make ethylene glycol and surfactants and so many other things. Okay, so very, very important molecule. Now, let us try and understand a little bit about there's something instructive in this whole process. Typically, when we talk about catalysis, it's a catalyzed reaction, and it is catalyzed by silver. And you can see these are islands of silver on a alumina catalyst. So the support is alumina, and these are all silver metals. Look how discreetly they've been put over there. Normally, we of course say high surface area catalyst. Of course, like for example, zeolite. People say it's got a very high surface area. Zeolite is a great catalyst. Yeah, it's a great catalyst for certain applications, but certainly not for example, making ethylene oxide. Because what happens is that if you have a very porous structure, let's say I have a very porous support, and some of the silver, etc., we'll see how it is made, the silver metal islands. When they're making it, some of it can get inside the pores. And so not only will it be on the external surface of the catalyst, but it can also be inside. Now the problem is that when I put in something like ethylene maybe it's a straight chain molecule, quite small, but once it forms ethylene oxide, the molecule may not be able to come out. So it can get in, but it can't come out. And getting in and getting out are as important, because unless I can regenerate my catalytic surface, it's useless. And second, if my the primary product that I form, if it undergoes further unnecessary oxidation, which it certainly will, things like this, then it's no use. So over here, what they do is that they take an alumina which has got a very low specific surface area, so that all the silver is only on the external surface. So that's what they do. And mind you, it's quite a high concentration of silver. It's 7 to 20%. So it's not a small thing. So obviously what you'll probably have is small particles of alumina, but maybe otherwise quite dense with very little porosity. And then you can load quite a bit on the external surface. What is also very interesting is that, when they were doing this study, and what they found is, doesn't matter how well you do this, they could never, at least initially, they could never go beyond a selectivity of around 86%. That means only about 86% of the ethylene became ethylene oxide, and the rest of it, what they found is that it's forming carbon dioxide. So they couldn't control that. So this reaction was actually taking place, this reaction, maybe even this reaction to some extent. So we tried to rationalize that why does something like this happen? And so this mechanism was proposed. You remember when we talked about vanadium pentoxide, and we showed some of these adsorption on active sites. So this is like, let's say, your metal, which is these spheroids over here. So the oxygen comes and let's say you've got 6 silver and 6 of these O2s come, and so you are just forming a interaction between the silver and the oxygen, and possibly what that interaction does is that it weakens the oxygen molecule, so that maybe it starts looking more like an oxygen radical. At least the oxygens have got spread out, it looks like. Then what happens is that ethylene comes and sits on this, okay, and one oxygen goes in and the other remains adsorbed on the silver. So it's not as if both oxygens reacted. In fact, to that extent, writing this equation like this is actually not correct. It is, you can actually write it as 1 olefin plus 1 O2, giving you 1 ethylene oxide, not 2. So keep that in mind. So then what this proposed is that maybe what happens is that these, if the silvers are quite close in proximity, and ethylene can come and sit in a way that it is interacting simultaneously with 6 of these silver oxygen moieties, and it will get converted into carbon dioxide at one go, and it will regenerate 6 silver, so that the process can carry on. And therefore, they were able to rationalize. You can work it out. Altogether, there are 7 ethylenes, of which 6 of them formed ethylene oxide. So what is 6 upon 7 into 100?
So approximately 86%.
Have you seen this? Although these things sound great, it's oh great. Now, and you've rationalized the selectivity, but it is not that it has to be this mechanism. It could be some other mechanism. It might be a feel-good factor that this mechanism helps to rationalize this. But whether this is the true mechanism, nobody actually knows. It's not so easy to figure out. Now, here I'm not going to go through it, but the silver catalyst is actually obtained by decomposing a silver amine complex. That's how they get it. And that's why you need to ensure that you don't have any porosity in your support, because the silver amine complex might get inside the pores, and then it forms the islands over there, and then you find that the ethylene oxide is not coming out from the pores that readily. So that's always a problem. You can also see that it's such a complex reaction, but even then the catalyst life is something like 2 to 5 years. It's really good. As we have learned in all of these processes, there are promoters which help to enhance the selectivity. This mechanism need not be strictly true. There could be competing mechanisms which help to increase the selectivity to something like 90 to 92%, which they have been able to find today. I've just shown you here the temperature and the pressures at which the reactions are done. So it's between 10 to 30 bar and 200 to 300 C. And remember, you're talking about moderately high temperatures, and how important it is to be able to control that the ethylene oxide remains stable. Now, I'm not going to go through the details of it, but I want you to see it. What happens is that you are really, you can actually do it in 2 ways. You can actually do an oxygen-based process where you take pure oxygen as the oxidizing agent. On the other hand, you can take air as the oxidizing agent, but if you take air, then obviously air has so many impurities that you have to first purify the air. Now, there's another thing very, very interesting about this particular catalyst bed. It's a catalyst bed. This catalyst bed has thousands of capillary-like tubes, hollow tubes inside. And the reason is because ethylene oxide formation is an exothermic reaction, and also you know that some amount of carbon dioxide formation is inevitable, and that releases huge amount of heat. So to be able to control that heat extraction is vitally important. So what they do is they have got these tubes and they coat the insides of these tubes with the catalyst. And so they get an extremely high surface area because of that. And secondly, because these are multiple tubes, so the heat dissipation from this, whatever heat is produced, is extremely efficient. And that is vitally important to the process. So really, this is where all the chemical engineering comes in. To be able to design what would be the most efficient way in which you might want to prepare your catalyst bed. So this is a completely different tubular type of catalyst bed. Ethylene oxide is soluble in water. Remember also that ethylene oxide is isomeric with acetaldehyde. And some amount of acetaldehyde formation takes place and some other side products also take place. So what they do is that after the ethylene oxide is formed, and actually you have also got carbon dioxide and things like that. So that is scrubbed with water. And so the ethylene oxide goes into solution and so does acetaldehyde. Even acetaldehyde is soluble in water. And then all the other gases, those are all taken out from the system after you spray with water. And then what you do is you do a distillation where the acetaldehyde is comes out, and ethylene oxide has a relatively high boiling point. So once the acetaldehyde and some other volatiles have come out, finally you can strip off the ethylene oxide from this. Whenever you're putting water, ethylene oxide always is vulnerable to hydration, hydrolysis. So ethylene oxide reacts with water and forms ethylene glycol. So there will be some glycol formation which will occur at this stage, and there will also be some glycol which will be formed at this stage. That's the glycol which will take off from your plant. So broadly, this is the way in which the ethylene oxide process is practiced. Now let me also tell you that another very, very important product which you get from ethylene. Okay. You remember we talked about acetaldehyde when we were talking about producing lactic acid. Acetaldehyde reacted with HCN and formed lactonitrile, which you hydrolyze to form lactic acid. The question is, where does acetaldehyde come from? Now, this is again a great process. Let me ask you, how would you want to make acetaldehyde? What would be your feedstock? What would you start with?
So ethane.
Ethane. And then?
Yes, sir. So and then oxidation of ethane. So
Better would be to start with methane and try to insert carbonyl, right?
yes, sir.
So that would be a great way to do it. Carbonylation of methane. I don't know if it's been done. That'll be worth, maybe you might want to check it out.
I had a small doubt. So
Yeah.
even in the production of lactic acid from ethanol, we did get acetaldehyde, right?
We took acetaldehyde and made lactic acid.
Okay, right. Okay.
Okay, of course you can also get it. I mean, I'm not saying that you can't by fermentation route, but normally the way acetaldehyde is made is by direct oxidation of ethylene. I should not say direct. Actually, we'll put indirect oxidation, not direct. Indirect. As we discussed, ethylene oxide and acetaldehyde are isomers. During the formation of ethylene oxide, small amounts of acetaldehyde are also produced. But people wanted to make acetaldehyde selectively. There's this company, Wacker, and Wacker were actually doing work, where in fact Wacker initially were trying to find an alternative catalyst to the silver catalyst. That's what they started with. They wanted to make ethylene oxide, but what happened was that Wacker showed that in the presence of palladium chloride, ethylene, gets converted into acetaldehyde. They did not succeed in making ethylene oxide, but it formed acetaldehyde. By the way, the Wacker process is the first known example of use of organometallic chemistry in industrial process. Let me also put that down. It's the first industrial process based on organometallic chemistry. Okay, and the one I showed you, the carbonylation, the Monsanto and Cativa processes came later. The Wacker process precedes those. That was an observation that they made, which is that that you take ethylene, you take palladium chloride, and what they were able to show is that it forms acetaldehyde. So what happened? This is the cat complex. Now you'll get quite savvy with this. I remember my professor in Princeton who taught us organometallic chemistry would tell us organometallic chemists will write the organic part of the molecule very small, and they will write the inorganic part, with the metal and all, big. And organic chemists, they will show you a small palladium and with a big organic molecule. And that's the difference between an organic and organometallic chemist. Obviously, this scheme was prepared by an organometallic chemist, not by an organic chemist. So what happens is, you take PDCl4. As I said, it has to dissociate so that you make it coordinatively unsaturated, and then the ethylene goes and binds to this. And then what happens is that water from here, it actually goes and attaches on one side, and you can see that this is a pi complex. Now it gets converted from a pi complex to a sigma complex. So this is a sigma bond, metal carbon bond, and on the other side OH got in. So you really added one OH, and on the other side got bound to the palladium. Then what happens is that again it forms a pi complex. So effectively it will again form an olefin here, like a pi complex over here. And now what happens is, again it forms a sigma complex, but not with the end. It forms over here. So the palladium has gone and got bound here. So then once that has happened, now again it goes and forms a pi complex, but this time it's the carbonyl which goes and attaches. You can trace this whole process, and what you'll find is that the palladium, which initially is in the palladium +2 state, gets reduced to palladium 0. Naturally, if ethylene is getting oxidized to acetaldehyde, then obviously palladium must get reduced to palladium 2 to palladium metal. That's effectively what happens. It forms palladium 0. It would have got stuck here. And after one cycle, it would have died, this process. In came Hext. Hext, as you know, is another great company. What Hext did was they discovered that if along with the palladium chloride, they add cupric chloride, CuCl2, what cupric chloride does is that it oxidizes the palladium 0 back to palladium 2. In other words, it regenerates this. And the cupric chloride gets reduced to cuprous chloride, CuCl. And then what they found is that if they expose the cuprous chloride to oxygen, it gets oxidized back to cupric chloride. Can you imagine this? So that's why I'm saying not direct, indirect, because the oxidation of ethylene to acetaldehyde happened with the palladium catalyst oxidation state change. Oxygen had nothing to do with that at that point. Oxygen came in when the cuprous chloride was reoxidized to cupric chloride, so that I can continue this whole cycle, and it goes and on and on and on. And it's the very famous process known as the Wacker-Hext process. Okay? It's easily one of the most elegant chemistries. And so that is how acetaldehyde is made. And now you know how lactic acid will be made from there. Now, let me also tell you, while this formation of ethylene oxide with silver catalyst was such a great achievement, which other olefin would you want to try out after ethylene?
So propene.
Propene. Okay, absolutely is the next higher olefin. Now, you go to do this with propene, it won't work. It doesn't work, this process. The reason is propene is very vulnerable to the oxidation of this methyl group, which you don't have in ethylene. So the propensity for formation of carbon dioxide as the predominant reaction will be much more. So back to square one. This is the process which has been commonly followed for making propylene oxide, which is basically your chlorohydrin process, which you have learnt about. Instead of taking chlorine, people have also taken other hydroperoxides like cumene hydroperoxide, ethyl benzene hydroperoxide. You can do it with many. But this has been a major challenge. In fact, I happen to be in a committee where this is one of the projects that people are trying to do, trying to see if they can make propylene oxide with oxygen, not through this process. That has not worked so far. But let me tell you today what is considered to be the most elegant technology for making propylene oxide. You can do it with chlorine. You can also do it with these. But somebody would have said, hey, why don't I try out hydrogen peroxide? Hydrogen peroxide is also a very green oxidizing agent because once the oxygen goes, you're just left with water. So it's very nice. This company, Evonik, were the one who were able to develop this technology. And what it is that you take it's like a clay-based catalyst which is loaded with titanium silicalite. Okay, that's what it's called, TS1. And amazingly, TS1 very selectively allows H2O2 to oxidize propylene to form propylene oxide. And obviously, there's nothing better than that because you don't have to form this chlorohydrin and generate calcium chloride. What are you going to do with calcium chloride with all this waste? So, whereas look at the elegance of this. I'm just left with water after reacting it. So this is the process. You take propene, you take hydrogen peroxide, solvent they use methanol, they carry out the reaction, and presumably the reaction is carried out at elevated pressure because after that they do a decompression. There will be some amount of propene which will remain unreacted, so you put that propene back, and from here you get your rest of it, propylene oxide in methanol. The methanol can be recycled back in the process, and you've got your propylene oxide. I've given some of the consumption figures, etc. I'm not going to go into the chemical engineering aspects of this particular bed. Is extremely interesting, and again, in this case, it all depends on this very efficient way of extracting heat. I don't know if you have been taught, but in this particular case, they say that the reactor is made with an ideal plug flow characteristic. If you are not familiar with plug flow, in any case, you'll learn it. If you have not already learned it, you'll learn it in the next courses which are taught to you. But you can also go and look at this video. Let me again take you through another very important molecule, vinyl acetate. How would you make vinyl acetate? What would I do? Which two things would I react to make vinyl acetate? One would be acetic acid. Okay.
Vinyl alcohol.
Vinyl alcohol. Very interesting. Is vinyl alcohol a stable molecule?
No, sir. So it will tautomerize.
It will just revert, right?
Yes,
And it will tautomerize. So to make vinyl acetate is not that simple, but it's an extremely important monomer. Whether you're talking about coatings, paints, textiles, adhesives, the amount of vinyl acetate is used. And now with all this massive boost to solar energy. What they found is that the solar cells, if they are encapsulated in polyvinyl acetate, that they remain more stable, maybe from radiation damage and other stuff. So that is again a huge application which is emerging for vinyl acetate. So these are some of the applications, and a lot of people are trying to switch over because it's a relatively cheap monomer. I was just working out the figures yesterday. It's about 5.2 million tons is what was sold in 2020, and the business is worth about $10.5 billion in 21. This is again related to oxidation, and this kind of chemistry is known as oxidative esterification. So you can think of it as if, like you said, as if I'm forming a vinyl alcohol. Vinyl alcohol means, I have to introduce an OH group, so I have to oxidize my ethylene. So there has to be an oxidation. And if I could make that OH, and then this OH, I can remove a mole of water, and I'll form this. So conceptually, you were so right when you said that vinyl alcohol, absolutely, except that it's not a stable molecule. Again, like in the case of ethylene oxide, like in the Wacker process, this is done with oxygen. And look, palladium, not very different to the Wacker process. So these people used to obviously play around. Once you have got something right out, and this gives you vinyl acetate. It's called oxidative esterification. Remember, exothermic reaction again, and as in the case of ethylene, when we saw, if the side product reaction happens, this is of course far more exothermic. So in this particular case, two things actually save you. And this is where chemical engineering comes in, and where all of you with your brilliance, you can always improvise and improve. One is they studied the activation energies of this reaction and this reaction. Unwanted reaction, this reaction. Same thing you remember when we were talking about N oxide. The activation energy of this is much lower than this. 30.5 kilojoule per mole, and this is 84.1 kilojoule per mole. So things that are more thermodynamically facile doesn't mean that their activation energy will be lesser. It can be opposite also. This is a classic case. So obviously, if the activation energy of this is lower, in terms of temperature, what would you choose? Would you choose a lower temperature or a higher temperature to carry out the reaction?
So low temperature and exothermic reaction.
Low temperature, not so much for exothermic. That's of course one reaction. In fact, it's a good thing for that. But the low temperature you choose because obviously at the lower temperature, I'll be able to maximize the difference in the rates of the two reactions. You understood? Because my activation energy difference I want to exploit. Whereas, if I go to a very high temperature, I won't be able to take advantage of the difference in activation energy. You got it?
Yes, sir.
That's one. Second, you see, this reaction requires 3 oxygens. This requires half an oxygen. So obviously, if I'm trying to have this reaction, I will carry out the reaction at a lower oxygen concentration. So I'll keep the oxygen concentration quite low. The other advantage that I get keeping the oxygen concentration low is that you remember the upper and lower flammability limits, that I can go beyond the upper flammability limit, and therefore the chances of things like having an explosion can be reduced. So these are all the clever ways in which you can manipulate the particular process. Well, tomorrow will be the last lecture, so I'll have to probably cut short a few things. I may not be able to cover all the processes, but that's not important because there are thousands of processes. I just want you to get a feel for how people go about manipulating processes and coming up with wonderful results. All right. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.